All right, we are near the end of the semester now. We are on the very last of the laboratories. Of course, they're all dry labs these days because we can't actually take data, but this one, like the I2 case, wouldn't have involved too much laboratory stuff. A little bit more than the I2 case. We would have filled a gas cell with HCl using an apparatus, and then taken a spectrum on an IR spectrometer. That's not nothing. It would have been useful to be able to do that, but all right, we are where we are. All right, so this time we're looking at the vibrational spectrum of the hydrogen chloride molecule, HCl, and the difference between taking the spectrum of I2 with a UV-Vis spectrometer and taking the IR spectrum of HCl is due to the fact that the HCl molecule obviously has a great big dipole moment. And that means that it's IR active, its vibrational transitions are IR active, and also its rotational transitions are IR active. And so we couldn't take, it probably would have been better to take the IR spectrum of I2 also. It's just that there is no IR spectrum of I2, but there is for HCl. So the analysis will be kind of similar. We'll go through the same kinds of things in the rest of this little lecture, but there will be major differences, and the biggest difference is due to the fact that we're going to be dealing with lower energy photons, smaller energy transitions between the vibrational levels and the rotational levels, not between the electronic levels. All right, so that's pretty much what I was saying before. This is saying what I just said. The transitions between the IR transition, the vibrational transitions and the rotational transitions are now IR active. And so if we draw the manifold for the ground state electronic level, we're not even going to think about the excited state now. It has all these vibrational levels. And on top of each vibrational level, there's a whole cascade of rotational levels as well. And that means that whereas before we could ignore the quantum mechanics of the rotations, this time we're going to have to take the rotations into account. We're going to see rotational transitions specifically. And we're not going to have to think about the electronic transitions at all. So it's similar, but using different sets of transitions, different sets of molecular energy levels. Yeah, so the transitions that we're going to be looking at are all going to be between the ground state vibrational level and the first excited vibrational level. We're never going to see anything higher than that. But between different rotational levels within each vibrational level, and these are, in fact, the transitions, or a few of the transitions that we're going to see. Further down, I'll talk about exactly what these lines mean and what these numbers mean and all, but we need a little bit of background before I can do that. Also, yes, as I said already, these transitions are all in the infrared photon energy range. The vibrational transition itself is within the IR photon energy range. And then we're going to see slight differences due to the rotational levels. So it's basically an IR transition, or a vibrational transition with structure, superstructure, that's caused by the various rotational levels. All right, let's talk about the quantum mechanics then, the energy levels. First of all, we're going to have the energy levels for the vibrational transitions alone. And that is exactly the same expression that we used last time. That should be familiar. Here is the harmonic oscillator contribution. This is the fundamental vibrational frequency. This is the vibrational quantum number, right? V goes between 0 and infinity in integer steps. And this is also the vibrational quantum number. And this is, of course, the anharmonic contribution or correction to the pure harmonic oscillator term. With the Morse potential, that comes from the fact that as the vibrational levels get higher and higher. The energy levels, a pure vibrational harmonic oscillator has equally spaced energy levels, but this is not a pure harmonic oscillator. As you get toward the top of the energy well, the Morse potential energy well, the levels start getting closer together, and this term, as last time, this term corrects for that. So we've got a harmonic term and an enharmonic term for the vibrations alone. And notice there are parameters that we're going to want to be able to get for both of those, just like last time. What's new this time is that we also have rotational energy levels. Here's the energy spectrum for that. There is a pure rigid rotor term that you get if you treat the molecule as not possible or not capable of vibrating or stretching. So rigid rotor means, yes, it's rigid. That bond length is fixed and can't change. If that were true, this would be the only term, but there's a correction term. And notice that there's some similarity here. Here it's V plus a half is a power or the quantum number in effect, and then it's V plus a half squared in the second term. Same kind of pattern down here. J times J plus 1. J is the quantum number, of course, the rotational quantum number. And it also goes from 0 to infinity in integer steps. And in the correction term, it's a J times J plus 1 quantity squared that accounts for the fact that, in fact, the molecule can stretch a little bit. So it's the lowest order correction for bond stretching. I have here a question mark about whether it comes from second order perturbation theory. I'm almost certain it does, but I haven't looked it up, so I can't be totally certain. For those of you who know some perturbation theory, then you have some idea where this came from. Otherwise, let's just take it as given. If we ignore this second term for now and just look at the first term, then the ladder of states looks like this. For J equals 0, there's just one state. For J equals 1, that occurs, you can see if I put a 1 in here, then I get a 2 from all of this, times a 1 over here, so I'll get 2 times HCB sub E. We'll come to this quantity in a minute. It's important. It has the molecular properties in it. But anyway, we get a 2 out here, and that's what this 2 is here. It's telling you how, relative to the ground state, how high the energy level is. And there are 3 states at that level. That's because there's a second quantum number, m sub j. If you recall back to Chem 311, and the rigid rotor has 2 quantum numbers. The energy eigenvectors are spherical harmonics. There's the j quantum number, and there's the m sub j quantum number. And just to put things in as simple a term as possible, these spherical harmonics are also the functions, and the quantum numbers too are also the quantum numbers that apply to the angular part of the hydrogen atom wave function. And so these quantum numbers should be familiar from what we know about hydrogen atoms. The J equals 0 ones are the s orbitals, the J equals 1 orbitals, well, J equals 1 eigenfunctions are the p orbitals, J equals 2 is d, J equals 3 is f, and so on. So we're looking in some sense at the hydrogen atom orbitals also. If you choose J equals 2, then the relative energy is 6, and there are 5 possible states. Actually, let's put them in. -2, -1, 0, 1, and 2. Down here it'd be -1, 0, and 1 for the m sub j values. We're not going to, I mean, these m sub j values and the degeneracy of all these levels here comes in at the very end, but for the most part we can ignore it, because it's only the gaps in energies that matter to us as far as the peaks are concerned. And all these energies are at the same level, so the gap, they don't change the gap. For J equals 3, there are 7 levels, -3, -1, -2, 0, 1, 2, and 3. For J equals 4, there are 9 levels, or 9 states on the same level, and so on. You can also see that the gaps keep getting bigger, right? There's a small gap here, bigger gap here, still bigger, still bigger. And that means that instead of getting one peak, if all these gaps were the same size, we'd get only one peak, right? There's only one photon energy could cause this transition as well as this one if they were the same size, if the gaps were the same size. But since they're all different, it's going to be different energy photons and therefore different peaks in the spectrum corresponding to each of these gaps. We'll see that below. All right, to return to this quantity in front, again, too much junk here. So this quantity in front, which contains the molecular information, let's talk about that. That quantity B sub E is Planck's constant divided by 8 pi squared, the speed of light, and then the moment of inertia for the molecule. That's where the molecular information is. All these other things are fundamental constants. They don't tell us anything about HCl. But the moment of inertia of the molecule does tell us something about HCl. Specifically, for a diatomic molecule, it's given by the reduced mass times the bond radius squared. Of course, obviously here we're ignoring the fact that the bond can stretch. So this is for the rigid rotor, strictly speaking, but we're not going to worry about corrections to that. We're going to take this as a fixed quantity for this part of the calculations. The reduced mass is mass of one of the atoms times mass for the other atom divided by the sum, the total mass for both atoms. And there's lots to say about the reduced mass. It's actually an important quantity, but it's, for the moment, we'll just leave that. And if you take that reduced mass and multiply it by the square of the bond length, the equilibrium bond length, the little e stands for equilibrium, then you get the moment of inertia. That's what goes in here, and that's what gives you B sub E. Of course, we're going to measure B sub E and get the moment of inertia and therefore the bond length. That's going to be one of the goals of our experiment here. All right. Yes, I guess I'm looking at this comment I made here in the notes, and it's just saying that yes, because the moment of inertia is in the denominator here, as the bond length gets longer, B sub E gets smaller, and B sub E is the gap size, basically, or it's proportional to the gap size. So these gaps get smaller the longer the bond length is, or they get bigger the smaller the bond length is. And therefore, the gap size is important to the molecular geometry, helps us determine the molecular geometry. All right, then there's a second term, the correction for the fact that the bond actually does stretch, which is proportional to this coupling, well, not really a coupling constant, to this extra factor, this extra constant D, capital D, and then J times J plus 1 quantity squared. And that D, in the Morse potential case, is just related to the B sub E value for the molecule and also to the fundamental vibrational frequency for the molecule, which comes from the vibrational part. So, and that makes sense, right? Because D here is telling us that the bond actually stretches. It only stretches because of the vibrations. So the stretching effect should be related to the vibrational effects. And so, yes, there's a vibrational parameter or quantity that comes in the definition of D. All right. So if we can find quantities related to D and quantities related to B sub E, then we can find both something about the stretching of the molecule and about the bond length of the molecule. Then there is another class of terms that we're going to add, and that has to do with the fact that if the bond stretches a little bit, then its moment of inertia changes, as we set up above, but that also, therefore, affects the rotations, and so there's a vibration, therefore a stretching, can change the vibrations, and the way that shows up in the spectrum is that it means that the gaps between the rotational levels when you're in the first excited vibrational state are smaller than the gaps between the rotational levels when you're in the vibrational ground state. In other words, going up at a level in vibration means that we're vibrating more than we were, which means that the moment of inertia is a little different now. The average moment of inertia is a little different. That affects B sub E, and that affects this spacing, which affects the spacing between the peaks in the spectrum. So to account for that, we add this extra term. Well, what we really do is instead of talking about the B sub E value as if it were a fixed constant, we talk about an effective B sub E value, which depends on the vibrational quantum number. In other words, this term reflects the fact that the vibrational level will affect the behavior of the rotations as well. And so this alpha sub E quantity is another parameter we're going to want to get at, and it's the rotational vibrational coupling constant. It's the thing that accounts for the coupling between rotations and vibrations. Coupling means that the vibrations affect the rotations and vice versa. The rotations affect the vibrations too. All together then, putting everything together, we have an expression for the energy levels for our Ro-Vib molecule, our rotating and vibrating molecule. And I've labeled all the terms here. First, there's the simple harmonic oscillator term and the anharmonic correction due to the fact that the well isn't truly a harmonic well. Then there's the term for the pure rotation rigid rotor, and a correction for that due to the fact the bond can actually stretch a little bit. And then finally there's the fifth term, which is this rotational vibrational coupling term, and you can tell that it's there because it has the coupling constant present. So that's our full expression, fairly complicated now, that gives the energy of each level in terms of two quantum numbers, just two quantum numbers, 5 terms, but just two quantum numbers. One is the vibrational quantum number V, and the other one is the rotational quantum number J. There is also M sub J, and that will come in a little bit at the end, but for the most part, for understanding where the peaks are, at least, it doesn't come in, because it doesn't affect the energy. You can see M sub J doesn't appear anywhere in this energy expression, and that's because all levels with different values of M sub J, but the same value of J, have the same energy. All right, now, when a transition occurs between two of the energy levels in our molecule, not every transition is allowed. There are selection rules. I don't know to what extent that was talked about in 311. It varies. It depends on who taught the class and so on. But the selection rules are set by something called the transition dipole moment. Which we'll see again below. So that's why I bring it up. The transition dipole moment is often 0 for symmetry reasons, and when it's 0, the transition is forbidden. And that means for an ideal molecule that followed the theory exactly, you wouldn't see the transition at all. In a real molecule, it doesn't follow the theory exactly. There's always small corrections. It means that it's a very, very weak peak, and so compared to the allowed transitions, it gives rise to only almost invisibly small peaks in the spectrum. So the allowed transitions have non-zero transition dipole moments. The forbidden transitions have 0 transition dipole moments. Usually the transition dipole moments are 0 for symmetry reasons. It's usually symmetry that causes the transition rules, or the selection rules. In this case, I won't go through where this comes from. It's a long and complicated calculation. There are three selection rules that matter. The change in the vibrational quantum number going from the initial state up to the final state, so V equals 0, say, up to V equals 1, that change in quantum number, in vibrational quantum number, has to be either +1 or -1. That means you can go up from one level to the next higher level, or you can go back down from the higher level back down. But you can't skip 2 levels at once. For V equals 2 up here, That's not allowed. A straight transition isn't allowed. A transition from here to here would be allowed. That's only delta V equals plus 1. But a transition straight from 0 up to 2 would not be allowed. Likewise, delta J can only be plus or minus 1, and that means that if you have two rotational levels, so here's V equals 0, here's V equals 1, here's J, so J equals 0 is the same as this level. J equals 0 up here is also the same as this level. J equals 1 is the next level up. J equals 1 is also the next level up in the excited vibrational manifold. And what delta J equals plus or minus 1 means is that if I start at J equals 0 up here, I can go up to J equals 1 up there, but I can't go to J equals 0, right? Because that would be delta J equals 0. Or I can't go to J equals 2 up here either, because that would be delta J equals 2. So I can start at 0 and end up at 1, or I can start at 1 and end up at 2, or I can start at 3 and end up at, I can start at 2 and end up at 3, and so on. Or I can start at 1 and end up at 0, right? That would be a minus 1. So there's two different possibilities. One is that the delta J gets bigger as I make the transition. The other is that the delta J gets smaller as I make the transition. And we'll see that has a big effect on the spectrum. We'll talk about that before. That down below, that corresponds to the P branch, and this corresponds to the R branch. And a delta M sub J has to be 0, which means, if we go back up here, that if you're making a transition between two rotational levels, too much stuff here again. So if you're making a transition between two levels, you have to stay with the same M sub J value. So I erased all the M sub J values, but this would be minus 3, minus 2, minus 1, 0, 1, 2, 3. This is be minus 2, minus 1, 0, 1, and 2. To be allowed, you can go from 0 to 0, you can go from 1 to 1, you can go from 2 to 2, but you can't go from 0 to minus 1 or 0 to minus 2 or 0 to 1 or any of those other possibilities. The M sub J quantum number has to stay the same in the transition. Again, that's not going to have much influence here because we don't really use the M sub J quantum number in this analysis. All right, so putting that all together, here's the transitions that are allowed. If delta J is equal to minus 1, then, as I said above, I can start from J equals 1 here and go up to J equals 0. That's this line. Or I can start from J equals 2 and go up to J equals 1. That's this line. Or J equals 3 and go up to J equals 2 up here. All those correspond to delta J is equal to minus 1. And that's the so-called P branch. On the other hand, I can start at J equals 0 down here and go up to J equals 1. So that's this line. I can start at J equals 0 is the heavy line there. This is J equals 1, and then I have to go up to J equals 2, right, for delta J equals plus 1. And or I can start at J equals 2 and go up to delta J equals 3. All those are delta J equals plus 1. And that corresponds to the R branch. Formally, it is useful to point out that if I started at J equals 0 and end up at J equals 0, I call that the Q branch. It's forbidden. There really isn't a transition there, but it's useful because all the peaks in the P branch have to be at lesser energy, lesser wave numbers than the P branch, and all the peaks in the R branch have to be above the Q branch. So the Q branch divides the P branch from the R branch, and the overall effect is that you get a spectrum that looks like this. Here's the P branch, here's the R branch, here's where the Q branch would be if it were allowed. In fact, because there are extra correction terms that we haven't accounted for in our theory, the Q branch isn't quite zero. There is a little tiny peak there. In some spectra, I think you might even be able to see it, but we're going to treat it as if it's zero anyway. So the R branch is all at higher energy, P branch all at lower energy than the Q branch. And now we want to analyze this spectrum for all the parameters that are contained in that energy expression, this one that we talked about above. How do we do that? Well, with the I2 experiment, we did it by looking at differences between the peaks, mostly. And we're going to do the same thing again here. So if I take the difference between two different peaks, for the R branch case, that means that the initial J value is called J double prime. Again, I don't know why the double prime. That's a funny notation. But if we say that we start from J double prime, then we have to go up to J double prime plus 1 if we're going to be on the R branch, right? Because the delta J has to be 1. And furthermore, this final J double prime value has to be in the V equals 1 vibrational level, having started from the V equals 0 vibrational level. So that means that we want to take the energy starting from J double prime and V equals 0, arriving at J double prime plus 1 and V equals 1. We want to take the energy difference between those two, and then we divide by hc to turn this into a wave number, right? Energy divided by hc is wave number. So these correspond to peak differences. And now it's a bunch of algebra. We just plug in this expression for the various, for 0 or 1, or for J double prime or J double prime plus 1, do a bunch of algebra, and we get that the peak difference for the peak position, sorry, not the peak difference, the actual peak position, I take that back, for, these are not peak differences, that's wrong. These are peak positions. Sorry, I was saying the wrong thing. We're not looking at differences here. I hope that I don't confuse too many people with that now. That was just wrong. We are going to look at peak differences later, but not now. Anyway, if we look at peak positions, for J goes to J plus 1, and we're just going to call that nu sub J double prime here, then we get this expression. And there's no point in going through the details. You can see that it's quite complicated, lots of terms, but I will point out that there is a term that doesn't depend on the quantum number. There's a term that depends on the quantum number to the first power, one that depends on the quantum number to the second power, and one that depends on the quantum number to the third power. And there's a little coefficient in front of all those, not so little, but a coefficient that's in front of all those powers, and that coefficient is what we're after. Which means that what we're going to want to do eventually is fit this expression to the data for the peak positions with adjustable parameters. You could call this A, you can call this B, you can call this C, and you can call this D. And use solver or some other thing for making a third order fit to our data in order to extract A, B, C, and D, and from those get the values for all of these quantities that we want. We can do the same thing for the P branch, except now it's J double prime goes to J double prime minus 1. So it's j double prime minus, everything's the same except it's j double prime minus 1 instead of plus 1 in this term. Again, a bunch of algebra, and again, an expression for the peak position. That includes 4 terms, a constant term, a first, a second, and a third order term. Again, these coefficients in front of the powers of j double prime are the quantities that we can extract by doing a fit from the peak positions to a third order polynomial. All right, that's all fine and would work, and I guess I don't recommend people doing it that way because there's an easier way that we're going to talk about now, but it would work just fine. However, there is a trick that allows us to, instead of doing 2 different sets of fits, just do 1 set of fits, and that's to define a new variable, a new quantum number in effect, n, capital N, which is equal to minus j double prime for the P branch, and equal to j double prime plus 1 for the R branch. And if you do that and replace j double prime everywhere in our 2 expressions up above, then you get just 1 expression. Now we're going to be fitting our peak positions to n values, not to j double prime values. But again, we're going to get a third order expression, a constant, a first order, second order, and third order term with coefficients that we can extract by doing fits. And so we'd only have to do 1 fit. We do 1 polynomial fit, 1 polynomial third order fit in this new variable n, rather than 2, 1 for the P branch and 1 for the Q branch, and then this works for both branches simultaneously. So you can put everything, both branches at once, on 1 single plot and make the fit, the third order fit, just once. And that accounts for, that actually works better than doing things separately, because it accounts for the fact that a lot of the parameters for the P branch are the same parameters as for the Q branch, and now we've got just 1 set of parameters for 1 sort of giant branch, if you like, by making this variables substitution. Okay, so that's the general picture. We're going to basically measure peak positions and then fit the peak positions to a third order polynomial in order to extract all the numbers. We'll talk about how we extract the numbers and what that means actually later, next time. For the rest of today, I'm going to say a little bit more about using the rest of the data in our spectrum. So far we've only talked about peak positions in the spectrum, and that's kind of always the most valuable and first order data to use. But the peak heights also matter, and the peak heights are varying, and the question is, why do they vary? Here's the main reason why, this expression. Here's the peak height, or what's called the intensity, and it's proportional to 2 different things mainly. I mean, it's proportional to this wave number value out here too, but that doesn't vary much. There isn't very big range of wave numbers from here to here, so this doesn't do much. But there is a number that controls the population of each initial state. If I have a transition from an initial state to an upper state, the population in this ground state controls how intense the transition is. The bigger the population, the more molecules are in the ground state, is another way of putting it, the stronger your transition is. That makes sense. And then it's also proportional to this quantity called the transition dipole, or transition dipole moment squared. So the transition dipole moment itself is this quantity, and then you square it to get this factor that controls the intensity. It's beyond the level of this little lecture to talk about where this comes from. It comes from perturbation theory and quantum mechanics, honestly. But we will talk a little bit about what that transition dipole moment is down below. In the meantime, let's talk about the this population factor, that's easier to understand. The population factor is just the number of states for each J double prime level times the Boltzmann factor that controls how likely the population is to be in that level. So in other words, if here are some rotational levels, if I start from the ground state, in order to get up to the next excited state, I have to get energy, right? I have to put energy in. That has to come from the surroundings, and that means that it's less probable that I'll just automatically or natively find the system in this excited state, and even less probable that I'll find it up in this excited state than the probability that I'll find it in this ground state. So ground state's most probable, next excited state is less probable but still more probable than the next excited state, and so on. And that's accounted for by this Boltzmann factor from statistical mechanics, from chemistry 312. The net result, all right, so it's less probable that you'll make the transition, but there's 3 states here, and there's 5 states here, and there's 7 states in the next level, and 9 states in the next level. So there's more states to occupy, and that also controls or affects how likely you are to be found somewhere in this whole level rather than just any one state. And the net result is the probability, or the product of the number of states in each level times the probability of being in that level at all. And that gives you a curve that looks something like this, this mountain with this peaked curve here. And you can see that peaked curve looks a fair amount like the envelope for either the P branch or the Q branch or the R branch. And so that's the explanation for the peak intensities, or for the population factor in the peak intensities. What about this second factor? It turns out this doesn't do very much. It's almost all this population factor, as we'll see. But let's look at that second factor. M sub j is the transition dipole moment for a pure rotational transition in this case. And that's equal to the wave function for the excited state, a dipole moment operator, the wave function for the ground state, and that turns out to be this integral. And after you do that integral, you get the following expressions. So this is m sub j squared, actually. And it turns out that unless j double prime is equal to 0, both of these also don't make very much difference. That's what I was saying up above, that most of the thing that controls the shape of these intensities is this population factor, this one down here, namely this curve here. All right. Altogether then, the intensity should be fit by this expression. So I've now plugged in the energy up in the exponential here. I've filled in the m sub j value and the population values for the R branch and for the P branch. And we won't use this to fit to the data. What we'll do is compare the predictions of this. All these values now, the B sub E values and so on, we will have gotten from the earlier part, which means we can plot this function with experimental values plugged in. We'll compare that to the actual intensities that we actually see and see how well we do. All right, the next section of the notes here we'll talk about next time. It's a bit of an aside on how the FTIR spectrometer would work, but this semester at least we're not even doing the experiment. It's still a good idea to look at it because knowing how an FTIR spectrometer works is a very valuable thing. But let's skip that for this week at least and just go down the list of what we will be planning to do. Amy and I will be sending you data, 2 sets of data actually, one for HCl, one for DCl. And then you'll make a table of all the peak positions versus the rotational quantum number for the P and R branch, right? We don't do it versus the vibrational quantum number because it's always the same two vibrational quantum numbers, 0 and 1. That's the only option we have. HCl, chlorine has two isomers, two common isomers, which makes some difference in the moment of inertia, right? A heavier chlorine atom will affect the reduced mass and therefore affect the moment of inertia, which means that in the spectrum, there's all the peaks are doubled. There's a low peak and there's a high peak. The low peak is due to chlorine 37. The high peak is due to chlorine 35. And by looking at the differences between those peak heights, we can get some information about the abundance of chlorine 37 and chlorine 35. That's one thing, that's for later. But it's important at this point to say that you're going to collect peak positions for chlorine 35 separately from the peak positions for chlorine 37. In other words, your spectrum really has two spectra sort of buried inside of it, and you're going to collect separate peak positions for chlorine 35 and for chlorine 37. Then convert the J double prime values to N values, right? You're going to get J double prime values for the P branch and for the R branch. Using the formulas above, you can convert all those to N values. Then you can use a third order fit to extract these experimental values, these model values, and D. I mean, the third order fit works really well out to second order. Whether our data are good enough to actually get a good fourth quantity, the third order coefficient is a little suspect, and that third order coefficient is what gives you the D value. But you can try and see if you can get a good D value. And then next, use the average values of the peak heights for the chlorine 35 and chlorine 37 cases to get relative abundances of the two. Then use some of the expressions above. Equation 10 in the write-up, that's this formula up here. I didn't really talk about it much, but it's way up here. This one. Use this expression, this is equation 10, in the write-up, in the other write-up. You'll see it labeled equation 10 in the write-up. Use that relationship in order to get some more of the parameters and compare them to literature values. And then finally, make plots of intensities for the P and R branches and overplot them with the predicted intensities from our formula up above. And then finally, a few things for the discussion, but I think we'll talk about that next week.